The next thing we're going to do is look at how to calculate probabilities in a particular type of situation. If you think back to the examples that we've looked at up to this point, we haven't computed a single probability because we haven't talked about how to calculate a probability in general. Well, in order to calculate probabilities, we have to have a particular type of framework within which we're working. And so now we're going to focus in on a particular type of situation that is fairly straightforward, fairly simple, and it's probably the only, if you think about the probability, or the courses where you've looked at probability in previous coursework, either in lower level classes in college or in high school, then this particular scenario is going to be the one that you've looked at. And that is computing probabilities for sample spaces with equally likely events. All right, so let's look at the structure of this particular situation. So suppose that we have a random experiment that has a finite sample space, which I'll denote by cap S, and I'm going to list out the elementary events E1 through E cap N like so. All right, so this is the sample space. It contains all of the elementary events for the experiment, and the number of elementary events, the number of possible outcomes for this experiment is capital N, right? And so I have these N elementary events. And suppose that this random experiment is conducted in such a way, and so this is going to depend on the way we conduct the experiment, doesn't it? So suppose that this random experiment is conducted in such a way that the elementary events are equally likely. All right, in other words, that these probabilities, and so what I'm going to do here is denote the probability. Let me start over here in the middle, okay, right here. So this notation represents the probability of the kth elementary event occurring. And to keep the notation a little bit simpler and less cumbersome, I'm going to denote that probability by lowercase p sub k. So for example, P1 would be the probability that E1 occurs, so the probability that that elementary event occurs. P2 would be the probability that E2 occurs, so that elementary event. And so forth up to P sub n would be the probability that E sub n occurs. All right, so I'm defining this simpler notation here, right, to keep things more streamlined. And so we're supposing that the experiment is conducted in such a way that the elementary events are equally likely. And what that means is that we don't need to differentiate these probabilities by subscripts because they're all equal. And so we can dispense with this subscript. And so the common probability is then P. So the probability of E1 is P. The probability of E2 is P, and so forth, out to the probability of E sub n is P. They all have the same probability of occurrence. They are equally likely. And so when that is the case, when the experiment is conducted in that way, then we have a couple of results that are going to be very, very helpful to us. Number one, what is this value? What is this common probability? Well, the common probability is 1 over cap n, where cap n is the number of elementary events in the sample space. So if the experiment is such that there are 10 elementary events in the sample space, then and if the experiment is conducted in such a way that the elementary events are equally likely, then each of those elementary events would have a probability of 1/10. Okay, so very, very simple. So I'm sure that you're very familiar with that. Now the second result, all right, is also going to be familiar to you because this is how you would have calculated probabilities in more elementary classes. So let A be an event in S. So A is a subset of S, right? It's an event associated with the experiment. The probability of A, which again is denoted by this notation here, P of A, is given by this ratio. All right, so how do we calculate the probability of an event when the experiment is conducted in such a way that the elementary events are equally likely? Well, this probability is the number of elementary events that are in the composite event A divided by the number of elementary events in the sample space. So listing these two events on the same page, just to get them in front of us. Again, result 1 is that the probabilities of the various events are equally likely, and they're equal to 1 over cap n, and the probability of an event is equal to the number of elementary events comprising that event divided by the number of elementary events comprising the sample space. Now, the proofs of these results are fairly straightforward, right? And because this is a theory class, we're going to take a look at these proofs. And so the proof of result 1, and so remember we're approaching this from within this axiomatic framework. So the first thing I'm going to do here is I'm going to appeal to axiom 1, which said that the probability of S is equal to 1. Now, S can be written as a set, as the set containing all of the elementary events for the sample space. Now, we can think of this set as a union of elementary events. Okay? And those elementary events are mutually exclusive. And so by an extension of axiom A3, which said that if two events are mutually exclusive, the probability that at least one of them occurs is equal to the sum of the individual probabilities, by a natural extension of that to more than two events, we can go from here, all right, to here. So what this says is that the probability of this event, which is the probability of a union of the individual elementary events, is equal to the sum of the individual probabilities. But now remember that because the elementary events are equally likely, each of these probabilities is equal to p, right? And so this probability is equal to the sum, k going from 1 to cap n, of p. But now we're adding up a constant, p, whatever it happens to be, n times. And so that is just n times p. Well, now we have an equation that says that 1 is equal to n times p, and we're looking for p. All we've got to do is divide both sides by cap n, and we get the result. And so that implies that this common probability is 1 over n, which is what we were wanting to show. And so that is the end of the proof. And notice, how did we do this? We utilized axiom 1, and we utilized an obvious and natural extension to axiom 3. Now let's look at how to prove result 2. And so let's denote our event A as a subset of the sample space in the following way. So you'll notice that the notation is getting a little bit more cumbersome here, a little more involved. I've got actually two levels of subscripting. The first subscript is J sub 1, the second subscript is J2, and so forth, out to the last elementary event whose subscript is Jm, J sub m. And so I've got the number of elementary events that comprise the event A is denoted by, is equal to m. We've got m elementary events comprising A, and the actual individual subscripts, I can't call them just 1, 2, and so forth out to m because those correspond to particular elementary events. So I have to use a second level of subscripting, and so I'm denoting these subscripts by J1, J2, and so forth out to J sub m. Okay, so the probability of the event A can be written as the probability of the event A written as a subset of the sample space. Because these elementary events are mutually exclusive, again, now this says by axiom A1, it's actually by an extension of axiom A3, all right, so you might want to make that correction in your notes. So by an extension of axiom 3, we can rewrite this probability in this way. It's the sum of the individual probabilities, all right? Now, remember that because the elementary events are equally likely, each of these probabilities is equal to 1 over n. And so, where do we get that? Well, that was the result. That's what we just proved in result 1. Now, what are we doing here? We're adding up a constant. How many times? M times, right there. What's the constant? 1 over cap n. And so that is equal to m times 1 over cap n, or m over cap n. Now notice that this lowercase m, that is the number of elementary events in the event A. And cap n is the number of elementary events in the sample space. And so the probability of the event A, when the elementary events are equally likely, will always be equal to the number of elementary events and the event of interest divided by the number of elementary events comprising the sample space. Okay, and so that is the end of the proof. Make sure that you correct this in your note. This is by an extension of axiom 3. All right, and so what did we use? Well, we used the extension of axiom 3 to prove this. We also used the previous result, result 1, that we just got done proving. Once we prove it, we're free to use it. All right, and we get the result that we need. So we've proven these two very useful results that we can now use to compute probabilities in those situations where the experiment's been conducted in such a way that the outcomes are equally likely. Therefore, to compute probabilities of events for sample spaces with equally likely events, what we do is we count the number of elementary events that comprise the event of interest and divide by the number of elementary events in the entire sample space. Now, note that this result appears to provide the basis for the classical definition of probability, because how did we talk about, or what did we say the classical probability was equal to? Well, we defined it as the number of ways that an event can occur divided by the total number of outcomes possible. All right, and so that's the same formula. But does this provide the basis for the classical definition? So think about that. And here are some things to think about to guide you in your thinking. What does it mean to say that events are equally likely? All right, and what is the basis for saying that events are equally likely? Can such an assertion be verified, and if so, how? So with that classical definition, we said that that definition applies only when the elementary events when the outcomes are equally likely. All right, but what does that mean? And if we were in class, we would talk more about this. And perhaps we will on Zoom or something like that. But I'll leave that for now, and we'll move on to the next slides. So let's revisit our examples that we've looked at before, and with their experiments. And so let's consider the experiment of flipping two distinguishable, but now we're going to say, in addition, that they are fair coins, say a quarter and a nickel, and record the up faces. So we've already identified the sample space for this experiment. There are 4 possible outcomes. And now I'm going to say that the fairness of the coins, by saying that these coins are fair, that's going to imply that the 4 elementary events comprising the sample space are equally likely. Now, that actually requires proof, but we don't have enough machinery yet to prove that, but I'm just going to say that right now. Okay, we'll use this fact, that the fact that the assumption that the coins are fair means that, or implies, that these 4 outcomes are going to be equally likely. And so we can calculate probabilities of events of interest using the approach that we just looked at. So for example, if the event A is the event that we get at least 1 head, B is the event that we get no heads, C is the event that both coins show heads, we can compute the probabilities of these 3 events under the assumption that the coins are fair. And so using this approach, the probability of A, all right, of getting at least one head would be equal to the number of ways that that event can occur, which is 3, divided by the total number of elementary events in the sample space, which is 4. And so the probability of A is 3/4, or 0.75. The probability of getting no heads is going to be equal to the number of ways that that can happen, which is 1, right? There's only one elementary event where we get no heads, divided by the number of elementary events in the sample space, which again is 4. So the probability of B is 1/4, or 0.25. And then the event C, both coins show heads, so the probability of getting 2 heads, all right, the probability of C is equal to the number of ways that that can happen. There's only one, divided by the total number of elementary events in the sample space, which again is 4. So that probability is 1/4. Now, the next example, we're going to consider rolling a fair die and recording the up phase. So again, now we're assuming that the die is fair. And so so we've looked at this example in terms of finding the sample space. So the sample space consists of those 6 values, those 6 possible outcomes. And in this case, it's a much more direct result to see that the fairness of the die implies that the 6 elementary events comprising the sample space are equally likely. So each of these possibilities, each of these possible results has a probability of 1/6. Now, we looked at 4 events of interest. A was the event that we roll an even number. B is the event that we roll an odd number. C is the event that we roll a number strictly less than 4. And then D was the event that we roll a number no more than 4. All right, and so now, because under the assumption that the die is fair, the elementary events in the sample space are equally likely, we can compute the probabilities associated with each of these events. But let me just point out that if the die was not fair, we would not be able to compute these probabilities in this way. We would have to have more information, about something, about the structure of the die or something. And that would be a much, much more difficult thing to do. Okay, but in this context, the probability of rolling an even number is equal to the number of ways that that can occur. There are 3 ways, so 3 over the number of elementary events in the sample space, which is 6. So the probability of A is 3/6. The probability of B, getting an odd number, is also 3/6. The probability of rolling a number strictly less than 4 is equal to 3/6 because there are 3 ways that can happen. And the probability that we roll a number less than or equal to 4 is equal to 4/6 because there are 4 ways that that can happen. Now notice that I've left these probabilities, I've not reduced them. So I left these as 3/6, 3/6, 3/6, and 4/6. In an algebra class, you would probably have to reduce these, or in a lower level class, you'd probably have to reduce these to lowest terms. But in this class, that's actually a disadvantage because what we're going to be doing is combining these kinds of probabilities via sums and things like that. And so it's going to be beneficial if we leave them like this. I mean, you can certainly reduce them if you want, or you could write them as a percentage, or I'm sorry, as a decimal. You could certainly do that, but it is acceptable to leave them like this. Okay, now let's think about rolling 2 distinguishable and fair dice and recording the up phases. So we've already identified the sample space. It's the sample space consisting of these 36 outcomes. And again, the fairness of the 2 dice implies that these 36 elementary events are equally likely. And so we can use this approach to computing probabilities associated with this experiment by counting the number of ways that the event can occur and dividing by the number of possible outcomes, which in this case is 36. So we defined several events of interest. Event A was the event that the sum of the dice is 7. all right, written as a subset of the sample space. It had these outcomes. B was the event that die 1 is a 3, all right, and then C was the event that the larger of the two dice is no more than 4. So the probability of A, which is the probability of getting that the sum, or a roll where the sum is 7, is equal to the number of ways that can occur, and there are 6 of those ways, divided by 36. So 6 over 36. We could reduce that to 1 over 6, but remember, we don't have to. The probability of rolling 2 fair dice and getting a result where die 1 is 3, so if die 1 is the green die, what is the probability we roll the dice and die 1 is a 3? Well, that is 6 over 36 as well, because there are 6 possible ways that we identified before that can happen. And then the probability of C, the probability of rolling these 2 distinguishable fair dice and getting a result where the larger of the 2 dice is no more than 4, is 16 over 36. Now let's look at this experiment where we're selecting a family with 2 children and recording the genders of the children. So we've identified the sample space. We've got here 4 possible outcomes. Now, we need to know something about, we can't really, we're not saying that we haven't used the word fair here or anything like that, but what do we're going to make some assumptions here that are probably pretty doggone reasonable assumptions. So under the assumption that male and female births are equally likely and that genders of children born into a family are independent of each other, the elementary events in the sample space are equally likely. All right, and so we're not going to prove that, but it is based on the assumption that male and female births are equally likely and that the genders of children born to a family are independent of each other. So in other words, the gender of the second child is not dependent on the gender of the first child, and so forth. Subsequent children, their genders do not depend on the genders of the previous born children. And so based on those 2 results, and they're reasonable assumptions for the purposes of illustration here. Actually, the assumption that the male and female births are equally likely is not quite true, okay, but we're going to assume it's true. We're just going to pretend it's true. That's a better word. We're going to pretend it's true for the purposes of this example. Okay, so in that context, under those assumptions, then these four outcomes are equally likely. And so let's see, we define some events of interest. The probability that the couple has at least 1 boy, that's event A. Event B is the probability that the couple has 2 girls. And so the probability of A is going to be equal to the number of ways that they could get at least 1 boy, and that there are 3 ways. And then we divide by the total number of possibilities, which is 4. So 3/4, or 0.75. The probability of getting 2 girls is equal to the number of ways that they could have 2 girls, which is just 1, all right, divided by the total number of possible outcomes, which is 4. So the probability of B is 1/4, or 0.25. All right, so we have looked at how to calculate probabilities for those situations where a random experiment is conducted in such a way that the elementary events are equally likely. And we have used that approach to calculate probabilities for several experiments that we have specified and are looking at, all right, and shown how to apply or how to do those calculations. And so we're going to continue on in the next lecture video on ways of determining these kinds of quantities, still in this context of equally likely outcomes. The approach involves counting the number of ways that an event can occur and divided by the total number of ways that the experiment can end up. And as we look at more complicated scenarios, determining those counts, those numbers, is not necessarily easy. It's probably not going to be very efficient for us to try to enumerate or list out all of those possibilities. Because in many cases, and you don't have to get very complicated, in many cases the number of possible ways that something can happen is quite large. So it's not going to be feasible for us to actually list out or enumerate all of these different ways, and so we need some strategies for counting the number of ways that an event can occur and counting the number of ways that an experiment can end up. And that's going to be the topic of the next lecture video. So we're going to stop this lecture video here and continue on in the next video.